Okay, so now we're gonna move on to more equilibrium stuff. I received the people that sent me in their acid base uh, worksheet. I will be going over them tomorrow, Wednesday, and Thursday, and Friday, and get you up a grade for them. Thank you for doing them. And if I can, I'll try to get back some form of uh, how you did on each one of them. It's hard to download them, and grade them, and then upload them again. So we'll see how to do it. Hopefully you've kept a copy of them, and if you ever want to take a look of them, can. And when we get straightened out again, if you want to come by and talk uh, about what's going on with these problems, you can ask me because it's all fun stuff. Okay, so again, we're going to explore equilibrium, but this time in terms of solubility. And chapter 18 and one version of the book, I think it's chapter 19, another version. So if you have the book, you can follow along. um, you're going to see a lot of the same sort of uh, methods that we've been using for. Okay, first of all, so solubility. We saw solubility when we talked about precipitation reaction, double replacement reactions, where you take two salts, add them together, and they form a precipitate. In this case, calcium chloride with sodium carbonate from calcium carbonate and sodium chloride. And the precipitate is calcium chloride. And we went over this in 121. Now, it turns out that every ionic compound or salt is dissolves in water, even if it doesn't seem like it is. Okay, so even if it looks like you're forming calcium carbonate, there's probably still some that is soluble. Okay, actually, quite a bit could be still soluble, but you're seeing quite a bit coming out of solution. Um, so so one of these compound having water solubility less than 0.01 mole per liter is considered unsoluble. Which, I mean, 0.01 doesn't sound very much, but actually it could be quite a bit that's still soluble. Okay, so when we went over solubility with double replacement reactions, the way we decided what things were soluble and insoluble was following solubility rules. Okay. Uh, and now what we want to do is actually get into more quantitative aspects uh, of solubility, because there's some salts that are more insoluble than others. Okay, so and that's what we're going to do is look at the relative solubilities between ionic compounds. Right, this gives you places where this kind of stuff is studied, and if you do go into medicine or what, I mean, it's probably used in just about any kind of water solubility chemistry. Go into waste management or water management. I mean, you'd be using it, and here's some other things. So it is applicable quite a bit in the world of chemistry. Okay, so what we're going to be looking at is the ratio, basically, of what isn't soluble and what is soluble. So we got an example here. So the ratio of the solid to the ions dissolved. So when you put an ionic compound, it dissolves in water. It separates into its ions. Initially, when you put the salt in water, obviously there's no ions, and then it splits apart into its ions. So in this case, and again, we talked about this would be found in ionic equations. Calcium fluoride, when you put it in the water, splits into calcium and two fluorides. So as this occurs, actually some of those ions that form will reform back into the calcium fluoride. And eventually they'll come to an equilibrium where you'll have have a balance. Remember, equilibrium doesn't mean equal amounts of product and reactant. Equilibrium is when the rate of is where the rate of product is equal to the rate of formation of the reactant. So the reaction is going just as fast to the right as it is left, but the amounts can be, and really most of the time are different, the sides. Okay. All right, so we're going to be using molarity as a way of measuring, or we can use grams per 100 mils percent, and other ways, molality that we used before. We're going to be using a solubility product that's basically equilibrium expression. And solubility is dependent on temperature, so when we do find our Ksp, it is dependent on temperature and will change. So what we're going to do is usually make sure that we identify the temperature when we do these, talk about these equations. All right, so let's take a look at an example. Let's say I have some silver chloride and I put it in water. It turns out that very little of the silver chloride dissolves in water. In fact, it looks like none of it. By eyeball, it looks like none of it has dissolved, but actually some has. And so what happens is, again, you get some product and you get back to reactant. And what we can do is write a equilibrium expression, a product over reactant. Now, this similar to Kw for acids, bases, Kw for water. We're just going to write in terms of product. And why is that? Is because usually the reactant, since we're really looking at the insoluble property, is that usually there's a lot more reactant than there is product. And so what we can do is we can wrap it up into the the Ksp and just look at the amount of product. All right, so in general, we could write a formula. We have two ions. You have an anion and your cation and your anion, and they're associated subscripts. And then you put them in water and they split apart. Okay, and so it's similar to equilibrium. You're going to have a coefficient, and the coefficient will be used as an exponent. And you'll see that as we go along. Now, similar to equilibrium, when the system is not in equilibrium, what you can do is you can measure the Q. And if Q is greater than K, that means there's too much product and the reaction will move to the left. And if Q is less than K, the reaction will move to the right and make more product. Now, we are not going to be dealing with Q, but it's the same kind of is what we when we talk about equilibrium. All right. Okay. What we want to do is write KSPs. And so what we have here is equilibrium expression, different equilibrium expressions, barium sulfate turning into barium 2 plus and sulfate, calcium 2 fluorines, and so forth. And so what we're going to do is write the equilibrium expression. The equilibrium expression just looks at the product. So it's Ba2 plus times SO4 2 minus. For calcium fluoride breaks into 2F, so we put the 2 as exponent. And then down over here, this is the silver chromate. They get 2 silver ions and 1 chromate, so you put 2 above the silver, and then the gold chloride, you get this expression. So similar to equilibrium expressions. All right, so we're going to use molar solubility and not as our measure. And what we're going to do is that, right, so we're always going to expect that there's going to be some solid present, and that in fact, probably mostly solid. And what we're going to do is assume that the solution that is saturated. What that means is it's at the point that, okay, better explain saturation. Okay. All right. Now, so, okay, I don't know if you ever do it, but maybe you could try it if you want at home or whatever. You get a glass of water, and then you could take some table salt and add it to your water, stir it up, and the salt will dissolve. Okay, you add another teaspoon, stir it up, and it'll all dissolve. At some point, as you add the salt to your solution, it will stop dissolving well, it'll look like it stopped dissolving the salt. So you put it in there, stir it up, and it looks like it doesn't dissolve. At that point, what you have is saturation. That means the solution is saturated with the ions, and it just can't take up any more. So at that point, what's happening is if you add more salt, what happens is that salt, some of that salt gets dissolved, but some of the salt gets undissolved, and that reaches equilibrium when you get to that point. So, and there's a precise point of saturation, and that's what we're talking about, is the point. Where exactly does that point happen? And we're not going to get into that. But so if you add your salt and salt and salt, there is a point, there is an amount of salt that you'll add exactly to your solution that adding any more won't. And that's the point we're talking about. So we're doing all these equations at that point where it's saturated. Okay. And that point, what happens is you get equal amount of product being the rate of making ions is equal to the rate of making the solid product. So that's what's important about this situation. Okay, so we're going to do different kinds of problems similar to what we've done before. If we're given solubilities, we can find Ksp, and given Ksp, we can find solubilities. And we're going to do a couple of these problems. All right, so this is the way we've been doing it for in the past. We take the balance equation and then write the equilibrium law, write the ice table, and then go ahead and solve what we need to solve for. Okay. All right, so here's the first problem. At 25 degrees C, the solubility of silver chloride is 1.34 times 10 to the minus fifth molarity. Calculated the solubility product for AgCl. So what it's saying is that when you add, so this is the saturation point you could consider, is that when you add this much, when you have this much concentration of silver chloride, that's when, if you add any more, it won't dissolve. Okay, so you might be adding a silver chloride, less than this amount. Then finally, when it gets to this amount, you're at saturation. Any more that you add is going to not dissolve because it's going to turn back into product. So that's the key point. So the solubility is where saturation takes place. And so what we want to do is follow the Ksp. All right, so you have your initial, so you do is you take your silver chloride, put it in water. So basically all you have is your total amount here, 1.34 times 10 to the minus fifth. And there's no product yet, okay? Then what happens is some of this, so the silver chloride dissolves, breaks apart and dissolves, but only this much will be dissolved. Okay, so you increase the amount of silver chloride, and then at equilibrium we have this. Notice is that the silver chloride, we don't care about its amounts because it's not used in the formula. All right, and just like so, what you do now is you just do the silver times the chloride, and you get 1.8 times 10 to the minus 10th. Okay, so this means is Remember, this could be Ksp is product over reactant. So this is, you have one product per about 10 billion reactants. Okay, so it's pretty insoluble. Most of it stays as reactant. Okay, so now what we're going to do is go the other way. Start with the Ksp and figure out what is the solubility at saturation. Okay. So what we do is we write the balance equation as such. Okay, and then write the equilibrium expression. And we know Ksp is 1.3 times 10 to the 12 minus 12. He has to be given this. Okay, just look it up. And then you set up your ice table. All right, so when you put the copper iodide in solution, some of it will turn into dissolve as copper and iodide. And we don't know that amount, but we will figure that out. So you gain some of the product, and then that's to when it gets to equilibrium. Okay, then basically what we do is we set up the Ksp equals 1.3 times 10 to the minus 12 equals x squared. And so we get solve for x. And the molar solubility for both of them is the same because they are in the equal amounts of stoichiometry. Pretty simple. Okay, so we're gonna do another one where we're gonna find the given the Ksp, find the solubility, similar to what we just did, but this one we have the equilibrium expression is gonna be different, and also the ice table is gonna be slightly set up differently. All right, so you have calcium fluoride, so it's CaF2. You yield Ca2 plus 2F minus. Now this is going to be the thing that changes here. The equilibrium expression is Ca2 plus times F squared. And the ice table is for every calcium that's made, you're making 2 fluorides. Okay, so the equilibrium expression is going to be this kind of has two effects. I mean, the subscript actually shows up in two places. It shows up as the exponent here, and also as 2 down here. All right, and then we just go ahead and solve it. So you get your x times 2x squared equals the Ksp, and then go ahead and solve for k, and you get remember it's the Ca, so x is 2.2 times 10 to the minus 4th. Okay, so that means that's x, so that's for the calcium, and 2x is for the fluoride.